So to start off, can you give us a quick rundown on what exactly a photonic chip is? Like, I get that it uses light, but how does that actually work?
So it all boils down to photons. Yeah.
Photons.
You see, light is made up of these tiny little packets of energy called photons. And unlike the electrons that regular chips use, photonic chips use these photons to transmit and process information.
Huh. So instead of electrical signals, it's like light signals zipping around.
Exactly. And because photons travel at the speed of light, well, that means computations can happen incredibly fast.
Okay, wait, hold on. At the speed of light, like no lag time whatsoever.
Pretty much. It's mind-bogglingly faster than traditional electronics.
I can only imagine. But how did we even get to this point? Like, where did this whole photonic computing thing even begin?
It's a fascinating journey that starts with the invention of the laser back in the 1960s.
Ah, the laser. That seems like ages ago.
It was a game changer. Lasers gave us this ability to create a really focused, intense beam of light, and that was crucial for controlling photons, which is kind of essential if you want to use them for computation.
So the laser was like the first step towards harnessing the power of light for computing.
Precisely. Then came optical fibers.
Right, those things that carry data as light pulses over long distances.
Exactly. That was another huge breakthrough. Suddenly, we could transmit information at the speed of light over vast distances.
So we have lasers to create light and fiber optics to transmit it. What was the missing piece of the puzzle?
Merging that speed with the manufacturing capabilities of electronics, enter silicon photonics.
Silicon photonics. So that's like using silicon, which is the backbone of electronics, to manipulate light instead.
You got it. It was a brilliant fusion of technologies, but of course it wasn't without its challenges.
Yeah, I was about to ask, didn't previous photonic chips have some limitations?
They did. And that's where this new Taiji chip comes in with a really innovative approach. It all comes down to how it manipulates light using two key concepts, interference and diffraction.
Okay, interference, I remember that from our deep dive on waves. It's like how waves can either amplify or cancel each other out, right?
Right. And photonic chips use this phenomenon to create logic gates, which are like the fundamental building blocks of computation.
So they're kind of like the transistors in electronic chips.
Exactly. And they work by manipulating the intensity of light to perform logical operations.
Interesting. So playing with the brightness of light is like flipping those ones and O's.
You got it. Now, diffraction is a bit different. Imagine shining a flashlight through a narrow slit.
I think I've done that before.
Instead of a sharp line of light, you see a wider, more diffused pattern. That's because the light bends and spreads out as it passes through the opening. It diffracts.
Okay, I can picture that. So how does diffraction play into computation?
Well, you can encode data into the properties of light and then pass it through layers that diffract the light in specific ways. Each layer acts like a mini pre-programmed circuit, performing a specific operation based on how it diffracts the light.
So it's kind of like a mini circuit board hardwired for a certain function.
Exactly. But the problem was these diffractive operations were fixed. They couldn't be easily reconfigured, and that lack of flexibility was a major hurdle for photonic chips.
Okay, I see where you're going with this. So this is where the Tai Chi chip comes in and shakes things up.
You got it. The Tai Chi chip cleverly combines both diffraction and interference to create a system that is both fast and flexible.
Wait, so it uses both. How does that even work?
Picture this. First, data is encoded as specific optical patterns using diffraction. Then these patterns enter a device called a Mach-Sender interferometer, which uses interference to manipulate the light beams. This interferometer performs complex calculations. Finally, the output is decoded using another diffraction layer.
Wow, so it's like a carefully choreographed dance of light with diffraction setting the stage and interference making the magic happen.
That's a great way to put it. And because photonic computing can perform many operations simultaneously, it blows traditional computing out of the water in terms of speed.
So instead of processing things one step at a time, it's like a whole orchestra playing in harmony.
Precisely. But speed isn't the only advantage. The Tai Chi chip also boasts some impressive stats when it comes to complexity and accuracy.
Okay, I'm all ears. Tell me more.
This chip can handle a mind-blowing 14 million parameters.
14 million. Whoa. But what does that even mean, handling parameters?
Good question. Parameters are essentially the variables that control the complexity of an AI model. So the more parameters, the more sophisticated the AI can be. And 14 million is a huge leap forward for photonic computing.
Okay, so more parameters, more brain power, got it. But how does it actually perform? Like, can it compete with traditional chips in terms of getting things right?
Absolutely. In tests, it achieved 92% accuracy on image classification tasks.
92%. That's amazing. Especially for analog computing, which I always thought was less precise than digital.
That's a big deal. And it doesn't stop there. It's also incredibly energy efficient. We're talking over 1,000 times more efficient than even the most advanced GPUs